Hi, I'm Luke Kingsborough, a member of the TECHSCENE REU at Michigan Technological University. My mentors are Saleh and Dr. Bruce Lee, and I will be talking about increasing electron flow in smart adhesive gel, a preliminary study. To start off with, most adhesives only have one cycle and can really only be used in dry environments. If they get wet, then they lose their adhesive properties, and usually after one cycle, they can no longer be reapplied, much like if you think about duct tape. When it's wet, it cannot attach, and when after one use, it cannot be reused. To combat that, smart adhesives were developed to be able to turn on and off due to external stimulation like temperature, pH, electrical application, etc. And this on and off switch can be done multiple times throughout its life cycle. For underwater smart adhesive, inspiration was taken from sea mussels. Sea mussels utilize catechol in order to adhere to surfaces and attach themselves. And they can also turn off this catechol when they want to move to a different location. Also, additionally, catechol can be used underwater. But, this catechol chemical can also be found within other substances like dopamine, methacrylamide, or DMA. And when polymerized within a hydrogel, it gives the hydrogel adhesive properties and can be turned on and off with pH or electricity, which is basically a localized pH gradient or change. In previous research, it was found that 9 volts allows for the quickest and lowest work of detachment, but 9 volts can also create unwanted side reactions like hydrolysis of the water within the gel, or can even interfere with equipment such as the electrodes used to create the current. So in order to reduce the amount of voltage being applied, the conductivity of the gel can be increased using conductive material like carbon nanotubes or polythiaphthalic acid, which can be inserted into the gel or dissolved, or thiophan can be dissolved within the gel. Also, the amount of electrolyte within the gel can be increased using hydroxyethylacrylamide or HEAA as a polymer backbone, which is hydrophilic, which is hydrophilic, and will like to hold on to water more. This experiment was done using 3 different formulations, each containing HEA at around the same amount. The first formulation had 515 microliters of HEAA, and the second and third both contained 415. Additionally, the first formulation contained 12 milligrams of CNT. The second formulation contained about 4 milligrams of CNT, and the third formulation contained 10 milligrams of thiophan. Another important difference between, or I guess a notable difference between the first 2 formulations to the third formulation is that the third formulation utilized thermo-initiator in order to polymerize the gel, while the others used a photo-initiator and UV light to polymerize. So each formulations were tested for the amperage at 1 volt, 2 volt, 3 volt, 4 volt, and 5 volt. As well, each formulation was tested for its equilibrium swelling ratio and water content using the mass of the sample when swollen and mass of the sample when dried. These swelling properties values were compared against literature, or previous literature, which contained the MEA backbone, which is hydrophobic, instead of the hydrophilic backbone, hydrophilic HEA backbone. So figure 1 shows the average amperage for each application of voltage, and as the voltage increases, the current also increases, but it seems that the first formula had the highest amount of voltage for, the highest amount of current for each voltage point, except for 1 volt, where the third formulation, the tile film formulation, had the highest. And it's unclear whether or not the first formula containing 12 milligrams of CNT is actually statistically higher than tiofilm. And additional statistical analysis is needed to conclude that. Table 1 shows the average pH 3 swelling properties for each formulation. And this shows that the tiofilm formulation was actually able to contain the most amount of water at 95% water content with a swelling ratio of 20, which is markedly higher than the literature equilibrium swelling ratio and water content. However, further statistical analysis is needed to actually conclude whether it is higher. It just appears to be higher at this point. So all in all, it appears that tiofilm, because of its higher electrolyte content, just through its swelling properties, and the fact that at 5 volts, it's almost the same as the 12 milligrams of CNT, that tiofilm appears to be the way to proceed with this experiment and for future studies as well. As a kind of reflection on this program and my time in the program has provided me with further understanding how to be a better leader by listening and being patient with other people, as well as knowing when it is time to stand up for things that are right. Additionally, they've also reinforced the idea that we should listen and ask questions before making assumptions about people's or procedures, and that this must be done before we can ever hope to be helpful. I would like to thank Dr. Rao, Professor Hadi, the TECHSCENE program, Dr. Val, for the opportunity to be part of this REU program, as well as like to thank Saleh and Dr. Lee for welcoming me into the lab and project and being patient with me throughout the whole process. Thank you.